Gio, what's that?
I'm not sure, but it sure felt like an earthquake.
Earthquake? What in the world causes earth shakes? Or earthquakes, anyway?
Well, Iggy, why don't we connect our databanks and I'll share everything I know about these underground rumblings with you.
Sure, as soon as my circuits stop quaking. I mean, shaking.
Iggy, let's think about the first thing you said, that during an earthquake, the earth shakes.
It seemed like the ground was shivering.
Well, the shaking you felt came from rocks moving underground.
I've seen humans shiver when they were cold. Did the earth get a chill?
No, actually, it's the heat of the earth that gets the earth quaking. The center, or core of the earth, is very hot, solid rock. Surrounding the earth's core is another layer of hot rock called the mantle. But this layer is a melted hot liquid that can move. Picture the earth as a big hard-boiled egg.
That would make quite a snack if I was ever hungry.
Now look at that thin layer on the outside of the egg, the shell. The shell is like the outer layer of the earth.
Are you trying to tell me that the earth has a shell?
Well, kind of. Actually, it's called the crust and is made of solid rock. This is the part of the earth we live on. Now take a look at this map of the Earth's surface. You can see where the crust is cracked into large pieces. Scientists call these pieces plates. The solid plates sort of float on top of the hot mantle.
It's sort of like a big jigsaw puzzle. The cracks are where the pieces fit together.
Right, and since they are on top of the hot melted rock of the mantle, the plates can slowly move against each other.
I'll bet the plates don't always move against each other smoothly.
You got that right. Sometimes the heat and pressure cause the plates to grind and shake when they move.
Making earthquakes.
Correct. But even though the cracks between these jigsaw pieces reach all around the world, their movements are only felt in small areas during any given earthquake.
And that's why a quake on one side of the world probably won't be felt on the other side.
Right again.
I'm loading all this information into my files, but let me make sure I've got it right. The Earth has a core, a mantle, and a crust. The thin, solid crust of the Earth cracks and moves slowly because of the hot mantle moving under it. The crust is separated into giant pieces called plates, and when these plates move against each other, earthquakes can happen.
You're getting the idea, but there's even more to learn about earthquakes. For one thing, all earthquakes aren't the same.
Some are stronger than others?
Yes, and there are different kinds of quakes.
Like what?
Actually, Iggy, I'm going to need a little help on that. My files aren't complete.
Then let's call up the Kids Into Doing Science Club for more information.
Hi, you've reached Kids Into Doing Science. This is Michael. How can I help you?
Good evening, Michael.
Hey, you two.
Michael, what can you tell us about different kinds of earthquakes?
Earthquakes are a very interesting subject. Let me get some images. Here you go. The separate plates that make up the Earth's crust can move in different ways. Like these bricks, they can move in opposite directions, side to side. One can slide up, or one can slip down. And these different movements underground can cause someone on the surface to feel different kinds of shaking. Like you see in this machine that recreates the force of an earthquake. The side-to-side plate motion creates the kind of shaking you would feel if you were standing on a skateboard and someone pushed and pulled it back and forth. The up-or-down motion underground creates the kind of shaking you might feel if you were standing on a trampoline and someone on the other side of the trampoline was bouncing up and down. And all of these motions can happen at the same time. up, down, and side to side.
That would be one crazy ride. Thanks, Michael.
Yeah, thanks a lot.
Talk to you two later.
Sometimes shifts in the Earth's plates not only create earthquakes, but they can cause mountains to form. One plate forces part of the other to rise.
Wow. But I bet those mountains didn't just pop up in one big earthquake.
Right. Little by little, shake by shake, over millions of years, these mountains rose. When the plates push against each other, the layers of rock bend and fold.
I get it. Like if you put a towel on a table and push it from both ends. It wrinkles up into ridges and folds.
Exactly. That's how the Himalayan mountains have formed in Asia over the last 60 million years.
Don't the rocks get pulled apart sometimes?
Sometimes they do.
Wouldn't that open up big cracks in the ground?
While cracks, called fissures, can form, it's pretty rare. The process of the Earth pulling apart is usually just as slow as when it pushes together.
Gio, I've been wondering, with all this pushing and pulling between plates, do earthquakes only happen along the edges of the plates?
No, they happen along fault lines too.
Fault lines? What are they?
Fault lines are weak areas in the crust that stretch out from the edges of the plates. Sort of like the lines that stretch out from a crack in ice. Earthquakes can happen anywhere along one of these cracks in the crust. Some faults are bigger than others, but even small faults have earthquakes. Which brings up a question I'd like to ask you. How many earthquakes do you think there are in the Earth's crust each year?
I'd say around 1,000?
Not even close. Scientists think that there are more than 3 million earthquakes in the world every year. More than 9,000 every day.
That can't be true. We'd be shaking all the time.
Well, most earthquakes are too weak for us to feel. There are less than 20 large quakes around the world each year that affect people. Of course, earthquakes not only affect the land, but the oceans of the world as well.
Wait, are you saying earthquakes can happen under the ocean too?
Of course. It's the land at the bottom of the ocean that moves when there's an earthquake under the sea.
I'll bet those make some pretty big waves.
They sure do. The Japanese gave a special name to the huge waves caused by earthquakes. They're called tsunamis.
Those kinds of waves could do a lot of damage when they reach shore. Gio, you said earthquakes are felt for only a certain distance. Why is that? I mean, earthquakes are so powerful. Why can't they be felt all around the Earth?
Iggy, the energy from an earthquake starts at one place deep underground. The spot on the Earth's surface that's right above where the quake starts is called the epicenter. The energy travels out from there through the ground in waves. It's a bit like ripples on a pond. If you drop a small rock into a pond, you'll see waves begin where the stone hits the water. The waves spread out in circles from there. These are waves of energy created by the rock when it dropped into the water. Scientists call the waves that pass through the Earth's surface seismic waves.
So just how does energy move through solid rock? I mean, rock isn't water, or a rubbery trampoline for that matter.
Anyone who has ever felt the ground shake when a big truck drove by has felt energy waves in the ground. It's the same thing with earthquakes, just bigger. Solid rock can bend when enough force is put on it.
So energy travels from the epicenter in waves.
That's right. And we can measure this energy. As you've learned, many earthquakes are too small to be felt by people, but others are very powerful. Scientists have found a way of measuring the strength of earthquakes. They give quakes numbers to describe their strength. The scale used to describe an earthquake's strength is called the Richter scale. The Richter scale runs from 1 to 10. Quakes in the 6 to 7 range have been known to shake cities hard enough to knock down buildings and flatten bridges.
But how do scientists figure out what numbers to give an earthquake?
They use what's called a seismograph. When the earth shakes, the needle of the seismograph marks a streak on a moving piece of paper. The bigger the shake, the bigger the streak.
That's pretty clever.
While a seismograph measures how powerful a quake is, scientists have other tools to study quakes. With special sensors placed in the ground, they can actually measure how the ground moves in an earthquake. Then they use computers to put together all their information to create a clear picture of how each quake acted. Scientists can also measure how the ground moves by using special lasers.
I'd like to see how that works.
Then watch.
This small shack may not look like much, but it's the center point of an advanced scientific network that measures ground movement near Mammoth Lakes, California. There's a lot of underground movement here, which often causes earthquakes. So what's in this shack? A very special laser light system. The shack is set on a mountaintop near the center of all the ground movement. Tiny mirrors have been placed at other locations around the shack, some as far as 8 kilometers or 5 miles away. The laser light is shined at the mirrors. The light bounces back from the mirrors to the shack. That allows scientists to measure just how far away the mirrors are. Then they take another measurement. If the mirrors have moved, that means the ground must have moved. Though these movements may be very, very small, the laser can measure movements as tiny as half the thickness of a pencil point. Now let's see the laser in action. Can you see that little bright spot of violet light? That's the mirror reflecting the laser light back. These laser measurements are taken about 3 times a week. Often, the biggest movements are discovered after there have been earthquakes. Over recent years, the mirrors have been moving apart at a rate of about 2 to 5 centimeters each year. That doesn't sound like much, but it shows definite underground activity.
Today, scientists understand a lot about earthquakes. They study clues that help them make better predictions. But it's very difficult to predict exactly where and when they will happen. This jigsaw puzzle of the Earth's plates can be helpful in predicting where earthquakes might happen. Places known as earthquake zones. One of the most famous earthquake zones lies on the San Andreas Fault in North America. Over 1,000 kilometers long, the fault winds all the way from Mexico to just north of California. For anyone who lives in an earthquake zone, the best thing to do is to be prepared. For example, take the Northridge earthquake, which happened in Southern California in 1994. Even though the earthquake happened under a large city, there were few lives lost. That's because the people of California were prepared. You see, the area had several strong earthquakes years earlier. They decided to make the buildings stronger and more able to withstand an earthquake. Fire departments and other emergency services were earthquake prepared and able to act quickly. Still, there were surprises. Some buildings did not handle the quake as well as expected. Work is being done to try to make these structures earthquake-proof. You've learned a lot today, Iggy. Let's review your databanks to be sure you've got everything.
Okay, I've learned why and where earthquakes happen. It's because the Earth's crust is cracked into giant plates that move little by little along faults. Sometimes, when the rocks of the crust shake and grind together, we feel earthquakes. Some earthquakes can hardly be felt. Others can do a lot of damage. And there are different kinds of ground movements in different quakes. The movements of the crust during earthquakes can cause mountains to rise and giant ocean waves to form. The energy from earthquakes travels in waves, and scientists can measure earthquakes using seismographs and other tools. So, someday, scientists will be able to predict exactly where and when earthquakes will happen.